Please, so we can hear you and we can see the slide.
Okay, good morning. My topic is Unit 3 plus image depth estimation, which I will use a modified Unit 3 plus model to estimate the image depth from an RGB image. So I will first introduce the background and my approach, and then I will talk about my result and I will conclude the presentation. So what is image depth estimation? As I said before, we use an RGB image to estimate the image depth. So it may require efficient models to understand spatial location and semantic class through monocular images. It is very important in various aspects, including like cave navigation, AR, and autonomous driving like Tesla. And it is very important to ensure the user's safety and comfortability. So there are some existing solutions for the depth estimation, like the LiDAR. It is very accurate, but it is expensive, and it works at a low frequency, like the 20 Hz. So it may not be applicable to some use case. And there are another product that is Intel RealSense. It is much affordable, but there are areas of blind spots due to binocular images. And I will talk about the blind spot at the later slide. So my solution is to use the Unit 3 plus model. It is originally for medical image segmentation, like here, and it has an encoder and decoder layer. The encoder is for extracting features and is usually a CNN, and then the decoder layer is some upsampling block to increase the resolution of the analyzed features. So the first generation introduced the plane skip connection, like what we have learned from the homework, and it append the same level information during upsampling to improve the performance. And then the researchers take it further to the Unit++, where the nodes are densely connected, but the model is too large such that the computation is too complex. So the latest Unit 3 plus model uses full-scale skip connections, which uses fewer parameters, while having a more position-aware and boundary-enhanced map. The hypothesis for the model being capable to tackle the problem is that the decoder near the output can capture the fine detail and sharpen the edge for the depth image, while the decoder further away from the output can recognize the general depth of a particular region of an image. So I will modify the Unit 3 plus model. The first modification is I will make it smaller because of my hardware constraint. And then the second modification is that the full-scale skip connection outputs a greater number of channels to the same scale decoder layer. So it is based on the hypothesis that the amount of unnecessary information from a different scale will increase. So to be more specific, a one-level difference causes a decrease in the number of input feature maps by a factor of 2, starting from 32 feature maps at the same level. So as an example, the right picture one is the modified unit, and it illustrates the layer calculation on the last decoder layer. So there is one low level difference, one level difference, and one 2 level difference, and so on. So the total feature map we received for this node is 32 plus 16 plus 8 plus 4 plus 2, and it is 62, which is different from the original Unit 3 plus, which is simply times 5 for the 16 feature map, and it got 18 feature maps for the last decoder node. So after looking at the model, let's look at the data set. I'm using the NYU2 data set, which the input will be the RGB with 3 channels, and the labels are the depth maps with 1 channel. All the images are normalized to 0 and 1, and I will apply random horizontal flip on them during training. So the loss function I use composes of 3 losses. The first one is the distance loss, which calculates the difference in the distance pixel-wise. And I will have the edge loss as well to calculate the difference in the derivatives so that we will have a clear and sharper edge. And the last one is the structural similarity loss, which I just import the library and calculate how similar the structure is, like the surface and different surface. And then at last I will have the accuracy function, which I round off the ground truth and the prediction to 0 and 1 and check if whether the 0 and 1 are matched for each pixel. So this is my result. After training the modified UNet 3+, I have a training accuracy of around 90% and validation accuracy at around 90% as well. And from the graph, I will tell that it works quite good with a little bit overfitting. And I will test its inferencing speed as well. And for a test batch size of 16, it has a total runtime of 0.004 seconds, which is very fast on average. And I think it is acceptable because it means that it can run at least 200 Hertz and it can be applied to some fast-paced environment like the autonomous driving. So when I compared the modified model with the original UNet 3+ model, my modified model has fewer parameters, while the training accuracy and the validation accuracy are similar, around 90%. But for the test accuracy, my modified model have 5% more in accuracy and 0.001 less in the loss. So I will call it a slight improve, but it is not significant. So I'll analyze the two models qualitatively as well. So you can see that it is the input and it is the ground truth label. And for these two models, you can find that my modified model can get more finer details like the 2-layer for the bookshelf here and the shape of the chair. But for the original UNet 3+, it may get the wrong distance for this chair. And then I compared my modified model with a larger and deeper model on the internet, which has 20 times more parameters. And it is a pre-trained DenseNet 169 as encoder, and the decoder connection is the same as the UNet structure. And the test result for this larger model, it has 0.03 less loss compared with my model and 5% more accuracy compared with mine. So you can see that the deeper model can even get even finer details like the printer and the surface are even smoother. And then I test the generalization ability of my modified model on a much different data set as well. And it is the car field data set. You can see that the ground truth is noisy and there is something like shadow. And this is the blind spot that I've talked about for the binocular depth image sensing before, and it is not good for training. But however, you can see that my modified model didn't do quite well, and it can just get the general structure, but the depths are mostly wrong. So to conclude, I think segmentation models are good at depth estimation tasks as well if trained properly, and a larger version or a pre-trained encoder can be used for better performance. But we may need to balance the inferencing time as well, as a larger model may have a longer inferencing time. And for the car field data, the model can be used as a pre-trained model, but the labeling is not clean enough, so it may affect the performance. And thank you. That's all of my presentation.
Yeah, thank you. Very good. Okay, so we have one question here. So did you check the inference time of the larger model?
Oh, I didn't check because I can't run it on my hardware. I would like to check it as well.
Okay.
I may try to check it later.
Yeah, maybe you can include this later in the final report.
Okay.
Yeah. So any more questions? Okay. So one more question. So how does the training depth look like?
Oh, training depth. Okay.
Training depth data look like?
Training depth data, I have shown it. I have plotted it as the different C map called color map yes, I have plotted it as a different color map, but I have improved it in the latest code. Just wait a minute. Oh, is it human neighbor? Oh, it is usually start off like this one. Usually start off like this one, and you can see that it has many noise and there are shadows because of the binocular calculation. So it usually requires human work to refine the label. So human labeling is required to cover the noise and fill back the shadow or the blind spot for the depth sensing camera. So after refining, we will get a beautiful ground truth like this.
Okay, great. So any more questions?
Yeah, and this is the better colored training data.
Very good, very good. Okay. So if no more questions, then thank you very much. It's a very nice project, and